Hello, everybody. This afternoon, I sent you two homeworks in one file, and I said I would have a video on that tonight. This is the video. We are working with binary trees. And if you remember, a binary tree has one root that has no parent, and every other node has one parent and at most two children. And if you start at any node with a value in it, everything to the right of it has a higher value, and everything to the left of it has a lower value. It's made for searching, and that's what we're going to do. Now, this is a new file, a new tree. The node of the tree looks like this. It has a value and it has a key. We will be giving a key to the search algorithm, and we want back the value that goes along with that key. When we read in a node, reading in the main line, I believe, yes, we're reading INK first and then V. So if you look at the data file, the key, INK, is 200, and the value is Joe. So in the methods for this particular bin tree, there is a method, getItem. You pass in the key, K. You pass in two variables that are going to be used for output. And this is it returns a pointer to a node. What we want back from this particular program is first where it found the node with this particular K, if it found it. If it found it, found will be true. If it did not find it, found will be false. And I not really care what node is. String V will be the value if it found it. If it didn't find it, I don't really care what V is. Now, the problem is that if you look at that, it calls another routine. This is because I'm going to pass in the root of the tree to getItem. That's going to be attached to the tree. And then from that root, I'm going to recursively go down the binary tree. That's the program you're writing, the recursive part of it in 13. You're going to get a key to look for, a node to start at, and the other things I talked about. The node at first is going to be the root, and then you're going to keep going. So basically your job is to look at the value that you get in that's pointed to by the node, and if the key is equal to that value, that node's key, you're done. If it's less than, you go left. If it's greater than, you go right. And you keep going until you get down to a point where whichever way you go is null. And in that case, you would say, it's not there. So it's a recursive program. And you've written a couple of recursive programs already with the count, and you've seen my add, which is in this program, which is also recursive. The second program I want you to write is to remove an element. Removing an element is not as easy as adding an element. It's still recursive, but it is a little bit harder. And I had been planning to send you this particular sheet here. I'm still going to send it to you, which has a website that shows the algorithm. But the website actually has the algorithm. It has it in C++, or at least most of it. However, it's not set up for your particular tree, so you'll have to adapt it to your tree. That's good practice, because often you find an algorithm that will work and you have to make whatever changes are necessary so it fits your particular case. Now look at the algorithm. I copied this from that site. There's an example of a tree, binary tree. There are some very easy cases for removal. If I told you to remove 13, then all you'd have to do is turn the left pointer, pardon me, I said 13, turn the left pointer of 15 to null. That's because 13 is a leaf. It doesn't have any children to worry about. So that's quite easy. Now also, if I ask you to remove 7, that's not that difficult. 7 has one child. So all you really have to do is promote its one child to where it is. So to get rid of 7, you just have to have the pointer from 5 point to 9. So the case of one child or no children on the node you're removing is easy. The question is what to do with 2 children. And there's the cleverness of this. Let's say we want to remove 15. We have to somehow get a value up there, and it has to be something that's reasonable. There are 2 ways to do it. I'll take this the easier one at this point. We look on the left subtree. The left subtree from 15 has 17 next. Now, anything less than 17 is going to be off to the left of 17. So we look at the left of 17. There's nothing there. So that means 17 is the smallest value in the left subtree. There's nothing smaller than it there. So the trick is you take the 17 and you replace what you're removing, the 15, with 17. Then you have a duplicate. You have 2 17s. But the second 17 has only one child. And that's an easy case. You just promote 20 to where that 17 was. So the final result, now they don't have it, but I think you can guess what it is. Now that's cleverer than some algorithms I've seen. The algorithm, maybe in your book, it's got all these things with going left, right, and right, left, and left, left. It's not as, I think, nice as this one. So I think you'll find that this one's easier to look at. Now, the last thing I want to do with this right now is the first part of this Notes 10, which I'm going to send to you. We're using binary trees. Why? We already have ways to represent ordered lists. We can do it either with a linked list, or we can do it with an array. Why binary trees? Well, the reason has to have something to do with the efficiency of the algorithms. So let's see. if we are representing the binary tree in a nice way, we want the tree to be bushy. That is, we don't want any long, straggling sections of it. We want most of the pointers in non-leaves to be filled in. So they call that bushy. I think you can understand. You just want it full. You don't want any long line of lots of blank pointers down that line. Well, if you do that, roughly the number of levels you need is log n, where n is the number of items in the tree. After all, if you have one element in the tree, that's level 0. We don't talk about, well, a log of 0 is 1. If you have 3 elements in the tree, that's level 2. And that's pretty, the log of 2 is, it'll be easier to, yeah, it's 1. Pardon me, I was wrong before. A log of 4, 8, whatever, we're always using base 2s. Our logs are log of base 2. Well, to find something in a tree, we start at the top and go down level by level. So it only takes us log n searches to find something. So that tells us that the algorithm is ordered log n. In an ordered list implemented as an array, the binary search is ordered log n. So they tied so far. In an ordered list implemented as a linked list, we have to search half the list on average. So the size of the list is n, and n over 2 is what we have to search. And so that's an order n algorithm. So the winner, binary tree, and array implementation. Inserting deleting. If we want to delete, we have to first search for what we want to delete. So that is an order log n, the search. And once we delete, it's a fixed number of things we have to do to delete it. So it sounds like that's order log n again. Insertion is the same way. So those algorithms are order log n for the binary tree. In an ordered list implementation, with arrays, well, we have to go down to find what we want. And so that's order log n, order n again. Using the linked list, we still have to go down to find what we want, and that's order n again. So the winner is the binary tree. So the winner, and not quite champion, because there's better approaches, the winner is the binary tree at this point with the ones we've seen. I will put these 2 items out within 4 or 5 minutes. Well, one of them's already out there, I think. But I'll put them out, and I'll put out this video, and then we'll see how you do. So long now.